Water is where you find it, not always where you want it. In today's world, a safe, stable supply of drinking water is indeed a valuable asset. Once a reliable source of water is developed, every precaution should be taken to ensure its longevity. However, what happens when good wells go bad? Just like good people who go bad, they need to be rehabilitated. Hi, my name is Tom Christofferson. I'm a water supply specialist for the state of Nebraska Health and Human Services System Water Well Standards Program. I will be your host for this video case history about a water well that went bad. The well in question was constructed in the early 1970s. Its purpose is to provide drinking water for a 4-H camp located in eastern Nebraska. In May of 2002, a water well rehabilitation workshop was sponsored by the Nebraska Well Drillers Association, Department of Health and Human Services, and the University of Nebraska Conservation and Survey Division. This video will illustrate the procedures taken to rehabilitate this well. These will include assessment of well condition, physical treatment, chemical treatment, development of the well, reinstallation of the pump, and the final results. The first step of the rehab process was to determine if it was feasible to clean the well or just simply replace it. Since no records detailing the well construction existed, we had to perform some detective work. This included a downhole video of the well. We also obtained water and sludge debris samples to be analyzed by a laboratory. Finally, we performed a pump test to determine the volume this water well was producing. A cost-to-benefit ratio comparing rehabilitation with well replacement was also studied. When these factors were all added up, it was clear rehab was the way to go. Seeing is believing. Come on, let's go take a look at what 30 years of wear can do to a well screen. Here we are on the morning of May 21st, 2002, 2 days prior to the workshop. Notice the discoloration of the mineral deposits covering the screen openings. These deposits have effectively blocked the water from entering the well. The incrustation of the screen openings can also contribute to the change of water quality of the well. Design Water Technologies, Shorewood, Minnesota, was chosen to analyze the water and sludge samples obtained from this well. Here are the results of water and sludge analysis performed by the lab. High counts of slime-forming bacteria combined with iron phosphates indicate the incrustation will present a challenge to rehabbing this well. Dave Hanson of Design Water Technologies served as the on-site expert for our rehab workshop. Dave is a nationally recognized speaker and an expert in the area of well design and rehabilitation. Having been associated with water wells and the problems that arise from water system operations since 1968, Dave was the obvious choice as guest lecturer for this workshop. Let's go see what he has to say about this well.
Hello, my name is Dave Hanson of Design Water Technologies. We're out here at a 4-H camp in Gretna, Nebraska. We're going to actually be showing you a series and methods of how to rehab a well. The particular problem in this well is a combination of iron bacteria and bacteria processing a certain iron phosphate as a nutrient. In any case of iron bacteria or slime bacteria problem in wells, it is extremely helpful to physically wire brush the casing and the screen on the inside and airlift and remove most of that debris. That does two functions for us. One, it then requires less chemistry to dissolve the amount of debris, and two, the chemistry is more easily able to penetrate through the screen and into the formation during development. This is a wire brush that we're going to be using, and it's an extremely stiff poly brush, and the reason we're using a poly brush is because we've got a PVC casing that is 6-inch diameter on this particular well. The reason we're using a brush is because if we can remove 30 or 40 or 50% of the debris in this well, that means that less chemistry would be required to dissolve that debris. What we can do in 15 or 20 minutes would take several hours for chemistry to do. We're making awfully good contact because you can actually hear the scraping going on. Now the wire brush has gone all the way to the static water level, and now we're going to be pulling the wire brush out. The bacteria that we have now loosened will not easily hang up on the wire brush, so don't expect that there will be a lot of debris on the wire brush itself. And this looks like a little manganese that has got caught up in the brush itself. Other than that, there's no debris there. What's happening right now is we're putting a 6x4 Fernco coupling on the top of the well, and that's so that we can put a T, and when we blow the debris out of the well, it won't make such a mess around the well casing itself. What we're installing now is the air line, and this will be used to airlift the airlift the well of the debris itself. And we're simply installing this by hand. What you're looking at now is simply a 4-inch T, and on the outside of that Fernco coupling. Now simply we're going to use an extended piece of pipe for the debris itself. What they're doing now is they've got all the adapters set up for the air compressor hose. We're using a rental unit. It's a 185 CFM air compressor, and now we're tying down with a chain the actual key itself, so that the air pressure doesn't drive it out of the well. We'll soon be starting the airlift pumping itself. We're now turning on the air compressor, and you'll start to see the discharge coming out of the actual 4-inch pipe itself. Notice how brownish the debris is. There's a lot of manganese in this well as bacteria. The debris is from the bacteria themselves is mainly a iron phosphate derivative, which makes this well so unusual. We had originally thought that iron phosphate was only found in maybe 0.1%, maybe 0.5% of all wells. Since we've started measuring phosphates in water, we've actually found it as a major problem in 3 wells over the last 6 months. So the feeling is that we might see iron phosphate as more of a problem than we originally thought. The reason iron phosphate is rather unusual and makes it more difficult, it takes a certain concentration of acid to dissolve an iron phosphate base. Generally, when using hydrochloric, that percentage must be upwards of 13 to 15%. When using something like unicid granular acid, that percentage must be at minimum 10% concentration. So in this particular well, we're going to be doubling the concentration of the unicid granular to dissolve that particular type of debris. We're going to be pumping this well till it starts to clear up, and it already looks like it's starting to clear rather nicely. What we're going to do is try to get some idea on the actual yield that we're actually pumping right now. The well was test pumped at 20 gallons a minute with about 10 feet of drawdown, so that's about 2 gallons a minute per foot of drawdown. We don't have any way of measuring drawdown in this particular situation, but we do have a way of measuring yield. One of the things that I'm noticing right here is a slight odor of hydrogen sulfide, the rotten egg odor that you traditionally find in some wells. When you have a lot of debris in a well, whether that debris be due to mineral scale or slime bacteria, The sulfate-reducing bacteria, which are anaerobic in nature, want to burrow underneath that debris for an environment to live. When the wire brush has scratched some of that debris away, we've exposed the bacteria, and then all of a sudden we're getting an odor. We filled a 5-gallon bucket in about 13 and a half, 14 seconds. Calculations are a little rough, but that calculates out to about 21, 22 gallons a minute that we're pumping. The odor is still present, so I think that we've exposed some of those bacteria.
Now let's look at the well after brushing. Note that a substantial portion of the debris has been removed from the well. But we find something that's not expected. The well had been sleeved with a smaller diameter screen, and this certainly complicates our rehabilitation efforts. The smaller screen won't allow our brush to reach the bottom of the well. To treat the lower screen, we will use extended surging and airlift development. Without this visual inspection, we may have damaged the lower screen with the surge block, or miscalculated the area of screen opening that needed chemical treatment. It's Thursday, May 23rd, day 3 of the well rehabilitation workshop. Today we will begin chemical treatment of the well. The chemical chosen to treat this well is a 2-part granular acid. The main reason being the well is encrusted with a mineral deposit, and analysis showed the presence of slime-forming bacteria. The granular acid itself works to dissolve the incrustation, and the catalyst has a biocidal effect on the bacteria. This 1-2 punch of chemistry should give us the knockout we're looking for. To calculate how much chemical is needed to clean up this well, we simply multiplied the diameter of the well by the feet of submergence in the well. Let's go back to Dave and see how to apply and maintain the chemistry by monitoring the pH.
In the cases where the thickness of the water itself is less than 100 feet and the static water level is less than 100 feet, in most cases you can simply pour the chemistry into the well, and when you start your surging process in development, we're going to talk about development later and how important and critical that is to the success of a job. When you start your development, the chemistry will become mixed as you go. We're placing the granular into the well first. The catalyst will go in next. And again, we're using a 2-product approach in this particular well because it does have a bacterial type of problem, and we want to make sure that we get in there and kill the bacteria. The catalyst is the product that can penetrate slime, it can penetrate debris, and it will kill the bacteria. About 500 to 1,000 times more effective than chlorine would ever be effective against slime-forming types of bacteria. The whole emphasis here is to get rid of the problem for good. In a slime type of application, we want to treat the entire column of the water, from the static water level all the way to the very, very bottom. That's going to make sure that all of the bacteria near the surface or near the static water level are as well killed and made sure that it's out of the well itself. What this is nothing but a piece of 5-inch PVC pipe with a plug and an opening on the top, and this particular piece of pipe has been filled with gravel, so it has a certain weight to it. The idea of the weight is when we drop it, it free falls. When we pull it up and drop it again, we'll get this nice surging type of action. He's now engaged the walking beam, and the nice thing about this is if we didn't have this, you would be standing there pulling on a lever, pushing on a lever, pulling on a lever, pushing on a lever. And we're talking about doing this bare minimum of 3 to 4 hours at a time, and then monitoring pH. So if you're pulling and pushing on a lever, you're going to get pretty worn out. This makes the entire process automatic without him doing anything. Now this gives us about a 3-foot stroke every time that's going up. And the speed of that can actually be adjusted by the RPM of just the truck itself. Maybe a lot of contractors don't fully understand. A pH of 1 means that it's very acidic. A pH of 11 means that it's something that's very alkaline. 7 is the neutral range. Most groundwater is somewhere around the 6.5 to 7.5 pH range. It's awfully nice to understand where we start from so that when we're done with this process and we're pumping all of the chemistry out, we know what pH level we need to get back to fully understand that we have all of the chemistry out. The ball check baler is sort of nice. We would normally run this down about into the middle section of the screen, and as the baler is going down, that ball check is up. And so when we get into a certain point and then pull up, that ball check seats, and the capture of the sample is from that particular area. And when you're using some form of a baler, try to take your sample at the same place each time, just so we have some representative sample of what's going on. Now in longer lengths of screen, if you had 40 or 50 feet of screen in a well, you might want to take it at a couple of different points, maybe 10 feet off the bottom and maybe 30 feet off the bottom, just to see if there's a variance in the pH area itself while you're surging. Yeah, get that one. That's good. Can you smell anything? No. Okay. We're starting to get a very acidic smell. It's a pH of 1.2 is where we're at right now. If development is not a function of your well rehab program, and you simply pour chemistry in a well and just let it sit there, it's not going to do very much, because there isn't a chemistry in the world that is like a smart bomb, that it goes down into the screen and looks out and say, aha, I can see scale out there, and then go after it. You actually have to push it out there. But the key to development is to make it happen in the areas where it's plugged. Now, if you can visualize a screen here, maybe 10 foot long, and you have the upper portion of it that is really plugged off. And if you're just airlifting, by lifting the chemistry up and letting it fall, or by doing it with a pump, pumping it up with, let's say, like a turbine type of pump in an irrigation application, for example, and you take the non-reverse ratchet off, and you lift the chemistry up and let it fall, the water, as well as the chemistry itself, will always follow the path of least resistance. The entire idea of doing this application with this type of development tool, this gives us the ability to use a surge block right in the screen itself, and we're forcing that action to happen much more aggressively and much more of a pinpointed action than we were by just raising it with air and letting it fall. What we're going to be doing now is running the baler back down into the well and then catch a sample of sand from approximately the same area that we took it this morning. So we've got a sample of the acid, and it's, I don't know, what color? Kind of a brownish green. kind of a brownish green color. And the pH is now at 1.4. We started out this morning at 1.2. The previous sample that Tracy had captured had a 1.3, so we're going up in tenths of a point in pH. That's a pretty slow rise. And I stand corrected. The pH is 1.7. So the pH is rising. The previous sample that we had, the pH was 1.3, and we started off with the pH this morning at 1.2. So the pH is rising. And we'll find out what it is in this afternoon before we leave the site tonight. Now, traditionally, what you would find would be a contractor doing a development for a period of somewhere around 2 to 3 hours, checking pH before he leaves the site at night. And if the pH isn't higher than, let's say, 2.5, we wouldn't adjust it. So if it was 2 or up to 2 in that pH of 2 range, we wouldn't adjust it overnight. We'd come back the next morning and we'd surge for about a half an hour, 15 to 20 minutes at least, just to mix chemistry up. And then take a sample of the pH reading and then adjust accordingly. So with this type of a rig and the amount of surging that we're getting done, we can actually stay on this longer to get more energy exerted down in the actual screen itself to get a faster reaction. Now tonight, or this afternoon, then we'll come back and measure this again, and if we're in the 2.5 range, we'll probably adjust pH later this afternoon and then surge in the morning and then check it in the morning.
Here we are. It's the moment of truth. It's May 24th, day 4 of the workshop. We have completed a full rehabilitation of this water well. Checking the pH this morning will tell us if the rehabilitation process worked. For example, last night the pH was 1.7. If this morning the pH has not changed more than 1 to 2/10 of a point, we will begin the removal process. There are a number of ways to remove these chemicals. We chose the airlifting process because as the chemistry is being removed, we are also developing the formation around the screen. Proper disposal of these chemicals at this site was not an issue. However, as with any chemistry, each situation is different and should be studied individually. Please be aware that the disposal of chemicals may involve neutralizing the chemistry before removing the acid from the well. Now it's time to see if our efforts were a success.
This morning, I would expect, and I'll probably be sorry for saying this, I would expect that the pH is going to be below 2, indicating that chemistry still doesn't have anything to work on. We'll still probably find a lot of silt. The other thing that could happen toward the end of a rehab process, you could actually see the pH skyrocket to 4.5 or 5 or 5.5. The foaming that you're seeing on the discharge is simply a combination of carbon dioxide and extra air that's being added to the chemistry itself. There's a tremendous sulfur odor, the old rotten egg odor that we're getting right now. And what's happening there is the debris is being removed and the bacteria are simply coming along with it. There's no more evident odor to the discharge, and the pH is now at 2.9. So we're still hanging in there pretty low. The coloration on the chemistry is now a lot lighter, and what will start happening as we continue to pump more and more water, that pH will just simply start rising. Now comes the issue of disposal. Now the question was put back to the 4-H camp, what do you want done with this chemistry? There's nothing in there that is hazardous. There's nothing in there that is reportable to any environmental agency. The combined chemistries are biodegradable in 27 days totally, but there is a pH issue. If you dispose any acidic chemistry, certainly below a pH of 5, it's going to be killing some grass and potentially some small trees and some weeds. They didn't feel that that was any issue here. The calcium in the soil will actually neutralize the acid. 28 days from now, there will not be any reportable environmental concerns or chemistry that would be found. You can expect to pump somewhere between 5 to maybe as much as 11 times the volume of a well before the pH will start to get close back to neutral itself. So if you have an environmental engineer that says how much debris or how much low pH product are you going to be pumping, you can give him some idea. Or if a municipality wants to understand exactly what's going on and exactly how much of the disposal issue might go into their sanitary sewer, they're going to want to have some idea of how much additional water is heading in that direction. You also want to have some idea as far as disposal from a pH standpoint. You certainly don't want to put this chemistry, for example, into a sanitary sewer. This chemistry will kill the bugs in a municipal sanitary sewer. If you do that, the municipality probably isn't going to be real happy with you.
Now that it's safe to visually inspect the well, let's take a look at the downhole footage. As you can see, the casing and the well screen openings have been restored to optimal condition. Even the section of smaller diameter screen in the bottom of the well has been successfully rehabilitated. In order to determine the degree of success of the rehabilitation process, a pumping test was performed once the visual inspection was complete. The results of the pump test are shown on this graphic. As you can see, we succeeded in improving the specific capacity of this well 280%. In 4 days, this well was restored to its original capacity. In comparison to re-drilling this water well, the drilling and development alone would take approximately the same amount of time. However, the plumbing, disinfection, testing, and final production would have taken an additional 4 to 5 days. In comparing costs, the required water analysis alone for the new water well would exceed the cost of rehabilitating the old one. When you add in the cost of drilling and installing the pumping system, the cost would have been 2 to 3 times the cost of rehab. Water well rehabilitation is a viable process to restoring a good water well that has gone bad. On behalf of the Nebraska Health and Human Services System, the Nebraska Well Drillers Association, the University of Nebraska Conservation Survey Division, Design Water Technologies, and the Eastern Nebraska 4-H Camp, I'm Tom Christofferson, and thank you for watching.